Today we are going to talk about variation of parameters. So we derived this method last time, or the special form of it that applies to second order linear ODEs. So we'll recall that it proceeds in basically 3 steps. So this is the method of variation of parameters. And so step 1 is that we find a fundamental set y1, y2 for the homogeneous version of the equation. Step 2, we find u1 prime and u2 prime by solving the system y1, y2, y1 prime, y2 prime, u1 prime, u2 prime is equal to 0, f. And remember, we're looking at the equation in the form y double prime plus p of x, y prime plus q of x, y equals f of x. So it's important that the coefficient on this y double prime here is 1. So that's the when we went through that derivation, we assumed we were in the standard form, and so this f of x is this f right here. So we solve that system. Now the entries here of this system, this is our matrix vector equation. The entries here are functions instead of numbers, but that's no problem because the steps that we go through in order to solve a system of linear equations works exactly the same for functions as it does for numbers. Well, practically the same. So there's no problem with that. And finally, step 3, we integrate u1 prime and u2 prime to get u1, u2, and use them to form the solution y equals u1, y1 plus u2, y2 plus c1, y1 plus c2, y2. So this part of it is our particular solution that we got by using this method of variation of parameters. And this was the general homogeneous solution. I think we were occasionally in the past referring to as y star or maybe yc. Anyway, that's it. That's all that we have to go through in order to do this. Now, of course, with the method of undetermined coefficients, we were solving a linear system, but it could possibly be a very large linear system. In this case, we're also solving a linear system, but it's only a 2 by 2 system. And but we have to do this step of integration. And so that might be the difficult step in this method. So we're trading some simplicity for some difficulty. But this also deals with the more general systems, because we can consider possibilities. In the other case, we were only looking at the situations where our coefficients were constants. And so in this case, we can consider situations where the coefficients are functions. We don't have to use the characteristic polynomial. So let's start off with an example. And this is one that I'm going to give you a chance to work out. I'll give you a couple of minutes to try to work this out on your own and then see what we come up with. So this one is y double prime minus 2y prime plus y is equal to e to the x over x. So I'm going to, I'll pause right here and give you a chance to try out the variation of parameters. Okay, you ready for me? All right. So let's see what I came up with. What did I come up with? All right, so first of all, I want to get a fundamental set of solutions. So a pair wasn't provided to us in this case, but it's no problem because we have constant coefficients here, and so our characteristic polynomial is r squared minus 2r plus 1. And so this has a double root, r equals 1. And so by variation of parameters in its previous incarnation, this shows that this is a very powerful technique. We get, well, first of all, we automatically have um, our first solution, so, sorry, R1 at Y1. And our second solution, which we got by variation of parameters, is going to be Y2 is equal to X e to the X. And we had previously seen, oh, actually, let me take a step back. So remember, this is something good to do at the very beginning here. Remember from our existence and uniqueness theorem that we'll have a solution wherever we have continuity. And our f of x right here has a discontinuity at x equals 0. So we have to assume the region that we're looking at is bounded away from 0. Either we're looking at the interval minus infinity to 0 or 0 to infinity, or some subinterval inside there, but we can expand it out to one of those whole ones. Anyway, we have to make sure that we're not including 0 in the region that we're looking at. And so for that reason, I'm going to just say that we're looking at this right here. If we had initial value, if we had an initial value for this, then that would determine which one of these intervals we're looking at. So in this case, we'll just look at positive x, so x greater than 0. Now we have a double root to this. We get our our fundamental set of solutions. So what we get from this is y1 prime is still e to the x, and y2 prime is, well, we've done this derivative so many times, we should probably have it memorized at this point, but I don't. So it's e to the x plus x e to the x, which we can rewrite as 1 plus x dx. All right. Now we can form our matrix vector equation. I'll put that right here. It's going to be y1, y2, y1 prime, y2 prime. So I'll put u1 prime here and prime here. And then we want to solve for these equal to 0 here and f here, which was, oh no, it's still on the screen. E to the x over x. Roll it away. Now we can simplify things a little bit by noticing that every entry in the matrix here has an e to the x, a factor of e to the x. We could factor that out. And our right-hand side, we can factor e to the x out of, well, we can factor anything out of 0. So we get that we can factor e to the x out of both sides, and so we get e to the x, 1 x, 1 plus x. And on the right-hand side, we get the x times 0, 1 over x. Now, by the standard way of dividing both sides by e to the x, because it's never equal to 0, we get this system of equations right here, which is a little bit easier to solve. And the determinant of this thing, which I'll call A, is equal to 1 plus x times 1 minus 1 times x. So that's just 1. The determinant of this is just 1. So it'll be easy to invert this thing. So we'll take the matrix, we'll divide it by its determinant, that's just 1, and then we'll swap the diagonal entries. Try to avoid the compulsion to make my 1s look fancy. So let's write it like that. And this is equal to 0 times 1 over x. Our left-hand side over here is now u1 prime, u2 prime. It's right on the right-hand side. And so what we get is that u1 prime is equal to -1. u2 prime is equal to 1 over x. Okay. So integrating, we get that u1 is equal to -x, and u2 is equal to, well, it would be the natural log of the absolute value of x, but we're only considering cos of x. So it's just the natural log of x. Now remember, we're using variation of parameters to get a particular solution. So there's a plus c in each of these cases. But we don't care about that because we're only considering a particular solution. So we can always just ignore that or consider c to be 0 in both cases. All right, so this gives us our two u's, our variated parameters. And so we can form the solution y equals u1 y1 plus u2 y2 plus c1 y1 plus c2 y2. Now I'm just going to rearrange things a little bit. I can factor in e to the x out of this whole thing. So I'm just going to stick that onto the end. And what I'm going to do is I'm going to write this as minus x plus natural log of x times x, which I'm actually going to write in the more standard way. For whatever reason, people normally write this x log x, plus c1 plus c2x e to the x. And notice that if I combine this with this, I factor an x out of both of these. Then I get c2 minus 1x, c2 minus 1x. But c2 minus 1, c2 is just an arbitrary constant. So if I subtract 1 from it, it's still an arbitrary constant. And so I can just fold that minus 1 into the c2. What I end up with here is x log x plus, I'm going to swap the roles of c1 and c2. They're just constants. They're just arbitrary constants, so it doesn't matter. So things look like they're in kind of descending order there. So x natural log of x plus some constant times x plus some constant dx. So this should be our solution. All right. Any questions about this? Pause for a minute. I really rushed through the material yesterday, so I'm going to try to go a little slower today. Okay, now just to stay in shape, let's see if we can solve this one using the method of undetermined coefficients. Well, should be a little more specific. Let's write this equation again. Do green this. Y double prime minus 2y plus 1. We've got constant coefficients equals e to the x over x. Now we had this trick of taking this e to the x and using it to get a new equation just in terms of u. So we were searching for solutions of the form y equals u times e to the x. Right? In this special eliminating the exponential step, we were looking for things of the form u times that exponential. So we're trying to get a ODE in terms of u, right? So I'm going to give you a minute to practice this, give this one a shot, and I'll come back and work this one as well. The same problem. Hopefully we get the same solution. Would you like some more time, or are you ready? You good? Okay. So let's take a look at this. We can get the characteristic equation. Well, the characteristic equation is exactly the same as it was before. So that's r squared minus 2r. I really screwed that up when I wrote it, didn't I? Nobody mentioned that. Okay. Thanks. I know I can count on you. So there's our characteristic equation. And this time we want its derivative. So that's 2r minus 2. And through the derivation that we saw a couple of days ago, we get an equation for u. We get an ODE for u that is, in this case, it's u double prime plus pi prime of alpha. In this case, or the constant on the x here, alpha is 1, plus, or sorry, times u prime plus chi of alpha u, and this is equal to 1 over x. So if we can solve this ODE, we have the solution. Because we can already figure out what the, let's go ahead and write this down again. Y1 is equal to e to the x, and y2 was x e to the x. And we got those from the characteristic equation, variation of parameters before. Okay, so plugging in alphas here, we get u double prime plus 2 times 1 minus 2, that's just 0. 1 minus 2 plus 1, again, that's just 0. So we get 1 over x. So u double prime is equal to 1 over x. Integrating this once, we get u prime is equal to natural log of x. Because again, remember, we're looking at just positive x, plus some constant, which I'll call c1, because I'm going to need to integrate again, and I'll get another constant. So u, we're going to integrate this. So this is the integral of natural log of x dx plus c1 x plus c2. Now, if you don't remember what the antiderivative of natural log is, actually, I have a point, but I'm gonna put that off for just a moment. So if we don't remember what the integral or the antiderivative of natural log is, we can use integration by parts in order to solve this. So that's a very important, very powerful integration technique. So if I'll go over here, have a little aside. I need to choose u, so something that I can easily take the derivative of. So that'll be natural log of x. dv in this case will just be dx. So du will be 1 over x dx, and v will be just x. So integration by parts, we get uv, so that's x natural log of x minus the integral of v du. So this is just x natural log of x minus integral of dx. So this is just x natural log of x minus x, which is equal to x minus 1. Natural log of x plus some constant. Okay, so this is x minus 1 natural log of x plus c1x plus c2. Now, it occurred to me as I was working through this that really I could just be ignoring these constants. So all of this right here, we're really looking for a particular solution. And what we're getting is like a general form for a particular solution. But we know that all of these particular solutions differ by some homogeneous solution. So we have, linear combinations of these two things. Now, when we multiply this out, we'll see we get the exact same thing. So all of this we could ignore because it's all going to be included in the homogeneous solution, or at least that's what we expect. So let's see what happens when I multiply this out. So y is going to be equal to, let me go back and write this as particular solution. So this is going to be x minus 1 times natural log of x times e to the x, which gives us x natural log of x e to the x minus natural log of x dx. Did I make a mistake somewhere? Yes, I made a huge mistake. This is actually a mistake that I've been making all morning when I was preparing for this. So, why not now? This should have been x natural log of x minus x, not x minus 1 times natural log. So that was a really bad mistake. My apologies. Okay, let's just get rid of this. And we're just ignoring all these constants right here. Okay, so our particular solution is x natural log of x minus x times e to the x. And so what we get for our general solution is this x natural log of x minus x e to the x plus c1 e to the x plus, and let's swap the order again, c1 x e to the x plus c2 e to the x. If I factor this out, again, I get x natural log of x. Now I'll combine the minus 1 again with c2, and I'll just get, or sorry, the c1, and I'll get c1x e to the x plus c2, well, factoring out the e to the x, c1 times x plus c2 dx. Okay. Now, setting aside all of the mistakes that I made while I was working on this, I think it's interesting to notice that this was, by all appearances, a radically different way of trying to solve the same problem. And yet we come to the exact same conclusion. Now, you've been taking math classes for most of your life, and so that's not such a surprising thing. But I think there's, if we kind of forget the fact that it's been drilled into us, math always works our entire lives. And it's kind of amazing to see that, two seemingly very different ways of coming to the same conclusion, but we do in fact come to the same conclusion. I don't know. I think that's just amazing. Okay. Next example. Now I'm gonna let you work on this one as well, but I'm gonna split it up into two phases. First of all, I need to tell you what the problem is. So it's x double prime minus 1 plus x times y prime plus y, that's our left-hand side. And our non-homogeneous term is x squared e to the 2x. So, well, like I did before, I have no idea why I'm making so many typos. I'm not typing, I'm writing rightos. The first thing I want to do whenever I look at this is I'm gonna try to well just mentally rewrite it in standard form, which means I'm gonna divide through by x. And so in standard form, let me write that out. In standard form, we get p of x is equal to 1 plus x over x, which has a discontinuity at x equals 0. So again, we're going to make the same conclusion that we're looking in the region x greater than 0. Okay. So like I said, this is a good step to check. We should check for discontinuities before we start so we know what the restrictions that we need to have on our independent variable will be before we go forward. So maybe I should add this to the 3 steps before. We'll call this a step 0 maybe. Okay. So anyway, step 1, we got step 0 out of the way. So step 1 is find a fundamental set of solutions to the homogeneous version. Now, the first thing you might notice whenever you start to do this is that we no longer have constant coefficients, right? We have an x here and a 1 plus x here, negative 1 plus x. And so it's a little bit trickier than it was before. So it might take a little cleverness, but I think that's a good thing to practice is trying to notice what kind of things you can deduce from this. So I'm going to give you a minute to try that on your own before I tell you a fundamental set of homogeneous solutions. Have either of you come up with any possibilities for homogeneous solutions?
I have a solution. I just don't know if it's right.
Okay,
so I probably made a mistake somewhere along the way.
It's possible. So what did you come up with?
I don't. Can you just like work it out? Because I really don't think I'm right.
Okay. Well, okay. So let's make a couple of observations here. So the first one is, I should say in the notes, they say that this is obvious. It's not so obvious to me, but we look at this minus 1 plus x here. If we were able to plug that in for y here, then we would get 1 plus x minus the 1 plus x, and it would cancel out. So that would be useful. It turns out that y prime is actually just 1. So you actually do get 1 plus x minus 1 plus x. And then the y double prime is 0. So that term just goes away. So that's the kind of idea that I'm thinking about here. And from that, we see that y1, 1 plus x is the possible homogeneous solution. So, right, it's not coming from a method, right? It's not coming from a series of steps. Now this other one, y2, this we can get from the observation. Well, let's just look at the coefficients on these. We have x, we have minus 1 plus x, and we have plus 1. And if we added all these up, we would get 0, which is what we're going for. So if we had a situation where we had y was equal to y prime was equal to y double prime, then this would also be a homogeneous solution. Well, there's a candidate that works for that, which is e to the x. And so that gives us 2 solutions. Just take a moment to just say, a very large part of success in mathematics is self-confidence. So there's no better way to build up self-confidence than just practice.
I got the e to the x, but I thought I had to factor in the negative sign in front of the 1 plus x. So I got negative 1 minus x for the first solution.
Okay. Yeah, so this one way of looking at this is that we're just making a guess. And then we can check the guess. And a lot of these things, like for example, when we were looking at that derivation for the variation of parameters method originally, and there were all of these things, and we saw that if we made all these assumptions at the beginning, once we got to the end, there was all this cancellation and everything worked out. And you might think to yourself, how did someone ever come up with something like that? Likely what happened is that they made just an educated guess at the beginning. They checked it with the equation that we're trying to solve, okay? And saw that the answer maybe wasn't 0, but it was something, it was off by some factor. And so if we go back and we tweak our initial assumptions just a little bit so that we can cancel out that error, then maybe we can work and get closer and closer to a solution. This is a very common way of approaching things in mathematics. Unfortunately, it's not the way a lot of math classes operate. This is one of the unusual situations where you're asked to do something without being told there's a method for it and just follow the steps. So, setting that aside, this is among all of the things that we do in a math class, this is the thing that is I think is the most important. Okay, anyway, that's our step 1. We found our fundamental set. Well, we found a set of solutions. We have to check and make sure that it is actually a fundamental set. And to do that, we will compute the Wronskian. And so the Wronskian will be, if we form this matrix 1 plus x, e to the x, and then the derivative, I'll just write out 1 y2 prime is e to the x again. Amazing property of e to the x. When we take the determinant of this, we get 1 plus x times e to the x minus e to the x. So this is equal to x e to the x. And what we want is for this thing to be non-zero. Now, if we included x equals 0, then we wouldn't have that. So we have this very fortunate observation that we made at the very beginning, which is that we're looking in the region x is greater than 0. That's not a problem. So our Wronskian is non-zero everywhere we're looking. Okay, now maybe, well, we've got 8 minutes left. Yeah, it's going to take a little while to prove this. So maybe I'll just continue this one myself. And you can try to outpace me. See if you can beat me to the solution. Okay, so step 2. Step 2 is solving for u1 prime, u2 prime. And we have our system of linear equations that will allow us to do this. So what is that system? That matrix that we formed before, 1 plus x, e to the x, 1, e to the x, times u1 prime, u2 prime is equal to, first entry is 0, second entry is f. And this is going to be x e to the 2x. That might have thrown you a little bit, because if we look back up here, we have x squared times e to the 2x. But remember that when we went through that whole derivation for variation of parameters, we did that with the assumption that this thing was in its standard form, which means we needed to divide through by the x. Now, when we're doing this variation of parameters, the only thing that matters is that non-homogeneous term. So it doesn't matter dividing this or dividing this by x. It's really just this part right here that we care about. We don't have to write everything out. We can just, gather the pieces that we care about. If you feel like you're likely to make less mistakes in doing this than I am throughout the entire lecture today. Okay, so we could solve this using any method of solving a linear system of equations that we want, but I'll just invert the matrix again, because we already have the determinant of the matrix. And so if we multiply both sides by the inverse, we'll get the identity on this side. Over here, there's an implicit I, an identity matrix, which is just like multiplying by 1. We get this vector here, and now on the other side, we get the inverse. And so it's dividing by the determinant. So dividing by the e to the x, I'll get e to the minus x, and then I'll write an x down in the denominator, just because it looks good. Other ways we could write that. Now I'll swap the entries on the diagonal, and then I'll negate the entries on the off diagonal. And I'll multiply this by the right-hand side. And this gives us our solutions. Well, our u1 and u2, the derivatives. Now I'm going to do a step of simplification. I'm going to multiply this thing through. But this time, I'm not going to multiply it into the matrix. We have a choice. We can multiply by either one of these factors. So there's the matrix factor, and then there's the vector factor. And what I'm going to do is I'm going to multiply it into the vector factor, because that's going to simplify things a little bit. So the matrix will stay the same. And the vector becomes 0. Now it's x, 0 times anything is just 0, so we're fine. 0 times anything as long as we're not dividing by 0, and we've already made sure of that. Okay, so 0 times this thing is just 0, and then x times e to the 2x. We're going to multiply that by e to the minus x, so we just get an e to the x. And then dividing x by x, we get a 1, so that's just 1 times e to the x. All right, now multiplying this through, I get the first entry, which will be u1 prime, 0 times e to the x, plus e to the x times negative e to the x. That's negative e to the 2x. Negative e to the x plus x. And the second entry, which will be u2 prime, will be 0 times minus 1, plus 1 plus x times e to the x. So this gives us our u1 prime e to the 2x, and u2 prime is 1 plus x e to the x. Okay, now getting u1 will be fairly easy. We just need to divide this thing by, when we take the integral of e to the 2x, just e to the 2x, but divided by the derivative of what's inside, so the derivative is 2. So this will be negative 1/2 e to the 2x. This u2 prime is a little more difficult. But I'll just use, again, that very powerful technique of integration by parts. So the thing that I'm going to take the derivative of will be the 1 plus x, and the thing I'm going to take the integral of will be e to the x dx. So there's our whole integrand. We rewrite it using the du here being just dx, the derivative of that, or the differential. And v is equal to just e to the x. So this will be equal to uv, 1 plus x e to the x, minus the integral of v du. So that's e to the x dx. And that gives us 1 plus x e to the x minus e to the x, which gives us just x e to the x. Okay. Now we get our solution. Well, we'll just get the particular solution, and then you can combine it with the general homogeneous solution in order to get the full solution. But anyway, maybe actually it would be good to do this all at once. So this is going to be u1 e to the 2x times y1. Now, what was y1? We decided that that was going to be 1 plus x, if I recall correctly. So that's 1 plus x, and then plus u2, which is 1 plus x e to the x, times our y2, which, if I'm recalling correctly, e to the x. Okay, so that's our particular solution. Now, this is just for the sake of building up our courage working with a situation where the coefficients are not constant, right? Everything will work in the exact same way. It'll be some arbitrary constant times our first homogeneous solution plus some arbitrary constant times our second homogeneous solution. So that's our whole thing. And we'll just notice now that we can rewrite things a little bit because we have an e to the 2x and an e to the 2x, a 1 plus x and a 1 plus x. And so what we have here is 1 minus 1/2 times 1 plus x e to the 2x for that particular solution. So this is, of course.
Wait, I have a quick question. For the U2, why did you use the U2 prime?
Did I use the U2 prime?
Yeah.
Well, see, that's because I make lots of mistakes.
Okay, I just wanted to make sure.
No, that's very good. It's good that you caught that because somebody had to. So yeah, no, that's just that's just me making mistakes. That's all. So this will be actually that's important because it gives us the right answer now. So we have U2 times Y2. You get the idea. Let's just change it back to original. We'll call the particular solution. And so now what I'll factor out the e to 2x. And then now what I have is x minus 1/2 x minus 1/2. And so we can rewrite this as x minus 1 e to the 2x over 2. I got to this point and I was feeling like, oh, finally, sort of woken up. And I'm not making these stupid mistakes anymore. Boom. Okay. Anyway, that's all I wanted to cover for today. Next time, we're going to talk about mechanical vibrations, which is just this sort of first example that you often see in calculus-based physics courses or mechanics courses. And it's this ODE that applies to a lot of physical situations. So we'll talk a little bit about physics stuff, and yeah.
Have a good day.
Thanks, you too.
Thank you.
Thank you.